So managing power factor becomes very important today, as I said. What is it? I'm an engineer, right? So we always learned in a book, there's a science book or a physics book, there's a definition, the ratio of real power to apparent power used in an AC power system. What does that mean, right, for most people? Particularly when you folks are trying to explain it to your business side of your company, the financial folks. What do you mean real and apparent power? Okay. Oh yeah, that's technical stuff. We'll come back to that. So it's very hard to explain. We had a bunch of folks in the class yesterday that said, yeah, you know, I've never found a good explanation to tell a non-technical business person what this power factor stuff is. That's important. Causes of low power factor. When we talk about managing power factor, we're really looking at motors, fluorescent lights, and LED drivers, or anything else with coils of wire and many electronic devices. How many of you have any of those in your plant? Yeah. They're a fact of life, right? The range of power factors in the market when you buy equipment is huge. So if I'm not looking, I might get really low power factor stuff that's a pretty good deal, and it could even have reputable brands on it. Why does the utility care? Bad things happen economically and physically if power factor is not managed and controlled and drops to a low enough level. Power factor improvement options, higher power factor equipment, power factor correction capacitors, or VAR compensators. Those are the options you have to consider in terms of if you have a low power factor and it's driving your peak demand, build demand up, what can I do about it to attack that? So what causes low power factor? Inductive loads, things with coils of wire or electronics. Motors. I mentioned oversizing motors gives me low power factor. Lots of small fractional horsepower motors. Fractional horsepower motors have terrible power factors. You cannot get a good power factor in a fractional horsepower motor. So that means if you have some lines that are run that have lots of fractional horsepower motors, what's your power factor at your plant going to be? Low. Just because of the fractional horsepowers that are on. Fluorescent and LED lighting systems. High efficient lighting can have high or low power factor depending on the quality. Solenoids. How many of you have lots of solenoid operated valves in your plants? Pretty common. Those all have a power factor. And those can range from pretty good to not so good. So you look at your plant, you can start looking and analyzing your situation to say, okay, what are the biggest problematic offenders potentially if I have a power factor issue that's low? So that becomes important. Why do power suppliers care? Economics. They want to match their revenue and cost more closely by customer. They don't want to have some customers subsidizing the low power factor of other customers. Reduce power line losses in the distribution system, reduce cost. So as we talk about more what it is, give you some visual images. Basically, when you have a low power factor, the utility has to provide you more reactive power than normal. And that reactive power means the amps go up that they're providing you above what it could be if you had a higher power factor. So as the power factor drops, they have to provide more amps on their system for you to utilize them. What does putting more amps on their wires do to their voltage loss? So if you supply the reactive power locally at your plant from the capacitors, the co-op no longer has to supply that reactive power in amps, and their line loss isn't as high, and their voltage is better. Okay, that's the big picture idea of, well, why does the utility care? Why does the power supplier care? Okay? So it's an economic and a reliability issue. If I improve power factor, I improve voltage regulation on the distribution system due to reduced line loss and voltage drop. Okay. So they've given you an economic signal, a price signal, an incentive on the bill that says you can pay us to do it, or if you want to manage it, you can do it on your side of the meter. But what is it? Okay, so I've talked about why, but what is it? Well, I gave you a science definition. Now I'm going to give you a physics definition. The deviation in the timing of the change of direction between the volts and amps in an AC system having coiled wires like motors and fluorescent lights. Yeah. Still, what is it? Right? I like to tell people this way. Now I've heard the analogies. The next slide is the analogies people use. You know, foam and beer and a horse pulling a cart down a track and all kinds of things. When I look back to Thomas Edison's days, the early days of the industry, when the only electric loads were incandescent lights and heaters, resistance heaters, power factor wasn't an issue. Incandescent lights and heaters, resistance heaters, have power factors of 100%. And so if you looked at the volts and amps in an oscilloscope, the volts and amps would track each other in time perfectly. They would peak at the same time in those sine waves and go through zero at the same time. As soon as I add a device that uses coils of wire and magnetic fields to an electrical system, those magnetic fields from those coils of wire start to slow the current, the amps, down in relation to the volts. It's what electricity does when we have coiled wires. Why are motors problematic? What do we do to make a motor? Windings. And the magnetic field in those windings causes the amps from the utility to start lagging behind the voltage in time. So now they don't go through zero at the same time and they don't have their maximum peak at the same time. That utility is burning fuel to make all those amps to go through their system. All of these amps outside the blue line here are reactive power. It's causing voltage drop on the system, but is no longer all that beneficial to you, the customer. Now notice, again, visually, graphically, if I go halfway between the blue line and the red line on the zero, the x-axis there, halfway between here, what direction are the amps flowing at that point in time, and what direction is the voltage trying to push? What happens in a water pipe if you have a pump trying to push one way, but the gravity is pulling the water back down, exceeding the pressure of the pump? Yeah, bad things can happen. So if this lag, which is really my power factor now, becomes too big, things get worse and worse and worse, and the utility's burning fuel at the generating plant to put amps on the system, causing a voltage drop that are really just taking up space out there. So the more low power factor equipment we put on the system, the bigger this lag of the amps behind the volts gets. That's what power factor is. It's caused by those things that have magnetic coils and electronics in your facility. Okay? So now the question becomes, okay, if by adding lower power factor things to my system, I cause the amps to start lagging behind the volts, how can I fix that? Okay. So in other words, how do I make those amps catch back up with the volts in time? And so the obvious answer is I need an electron speeder upper, right? That's a technical term, electron speeder upper. We call them power factor correction capacitors. So the power factor correction capacitor does the opposite to to the amps of what the motors do. The motors make the amps move lagging behind the volts. A capacitor is like boost. Okay? No F-150 folks in here? Okay? I want to speed that air up. Turbocharge. We're not going to call it a turbocharger, we call it a capacitor. If I put too much capacitance into the system, I can make those amps shift to lead the volts. So I don't want to just arbitrarily throw capacitors up there. I want to have the right amount. So I get close back to timing and don't overshoot too far. That's power factor correction. So based on your loads that are causing the amps to lag the volts, we want to put something in there that will essentially speed those amps up in relation to the volts and get them back closer to that which is the optimum. That's what power factor is, why it's important. Those coils of wire cause these amps to start lagging the volts in time in the system. Okay? So the math is the way engineers typically express it. That's the way every engineer learned what power factor is with math. So you'll hear people try to explain it using the math. A ratio between the real and apparent power expressed as a percent. So power factor is the kilowatts divided by the kVA. An example, if my real power was 500 kilowatts and my apparent power is 555 kVA, 500 divided by 555 gives me a 90% power factor. Okay. Or if you like vector math and trigonometry, I can use the Pythagorean theorem. Okay. Terry, there you go. Okay. I'm sure you asked at some point a professor, am I ever going to use this Pythagorean theorem junk? With power factor, it's really important. Okay? So I've got my apparent power, I've got my real power, and my reactive power. The math all works out, and power factor is the cosine of theta. We engineers like to essentially use jargon to screen all the rest of you out. Makes us feel good if we're talking about stuff you don't know about, you know, things like that. People say, you're an engineer, you must really love math. I have never found myself at a social function over an adult beverage talking about math. I was just patient enough, evidently, to do it. So why is this so confusing? Well, I could say because math is hard and people don't like to do math, right? And that's how we always explain power factors with math. Oh yeah, everybody likes trigonometry and cosines and sines and square roots of the hypotenuse and things like that. So immediately business people tune us out when we start talking like that. So it causes a disconnect between our billing and equipment sizing jargon. My graphic slide down here is a perfect example of that. When you size a transformer, what units of power do you size a transformer in? kVA, right there, 75 kVA. When that utility is measuring how much peak demand you're using, what are they measuring at that meter? Kilowatts. So we have a disconnect between our equipment sizing and our billing in the industry. And that dates back to the early days where power factor wasn't important. We have to make sure that that transformer has enough capacity to carry the total power going through it. The real power and the reactive power, which is the apparent power, and that's always measured in kVA, but historically those demand meters measured kilowatts. So a disconnect. That becomes confusing to people. So real power, kilowatts or megawatts, is used as a billing term, and apparent power, kVA or MVA, is used as an equipment sizing term. And the relationship between those two is, how do I go from one to another? I need to know the power factor in the equation, then I can work it out. This is no wonder people don't understand this in terms of this disconnect of our units and things like that and the math that comes with it. So all kinds of different people I run into around the country have tried to use analogies to explain this to their business people. Okay? Pulling a wagon, a horse, off to the side with a rope here, and the wagon's going down the track. There's our Pythagorean theorem again, the right triangle. And we're still back to cosines and angles and square of the hypotenuses or square roots. At least with my Texas A&M students, when I mention beer, the foam and beer analogy, when I mention beer, I've always got their attention for 30 more seconds. Okay? So we're talking about at least something that they can understand. Okay? And so I've seen the beer and foam analogy used by a lot of people. And when you do this with the business people, you talk about, well, you've got the foam, that's the reactive power. You've got the beer, that's the real power. And the total of the foam and beer, that's the apparent power. And so think about this. I've got a 12-ounce can of beer and I open it up. If I don't pour and manage it right, that 12-ounce can of beer won't fit in a 12-ounce mug. And pretty soon the business people says, I thought we were talking about electricity. Okay? So we use all kinds of analogies to try to explain this. I've never found good luck with any of the analogies in terms of getting business people to understand it. But when I go back to business people and I tell them, your motors and your lights and your solenoids in your plant cause the amps from the utility to slow down in relation to the volts. That's the physics. And you can put a capacitor in to speed those amps back up. That's physics. Most of them say, oh, okay, I can at least understand why we're doing that. I still don't know what power factor is, but it has to do something with slowing the amps down when we turn our equipment on. And if that slowdown is big enough, bad things happen, we won't want that to happen. So yeah, okay, I at least can talk intelligently now and understand why you're wanting me to spend money to put these capacitors in. If you can get them to that point, I think that's what they really want to know. Not what power factor is, but at least a definition that they can visualize. Oh, we're slowing the amps down when we turn our equipment on, that's physics. We can correct that by spending some money, and if we correct it, we don't have to spend as much money to the utility. That's how I like to approach it. So motors, induction motors operate with a power factor less than 100%. Some motors have higher power factor than others. That can be a part of your purchase decision. Somebody asked yesterday, well, how do you know what the power factor of a motor is before you buy it? There are databases and other things, online programs you can go, and you can basically look and say, for 100 horsepower, 3-phase, 460 volt motor, what's the range of all the power factors for all motors I could buy in the market? So if you can go to a database and look up and see what the motor power factors are, and what the high and the low and the typical range is, you have a better idea of what's good and what's not so good. Large motors generally have higher power factor than small. We mentioned that before. So I should just use large horsepower motors. Well, not necessarily, because when I oversize those motors or underload them, they're going to operate with a lower power factor. My worst case potential problem in a plant: customers with large numbers of fractional horsepower motors that operate long time periods, and they've oversized their larger motors. There's your customer that can have a really, really bad power factor in terms of if they haven't done anything to attack that yet. So the motor nameplate power factor. Today, most motors have it on the nameplate. A lot of times the struggle with doing energy audits 20, 30 years ago was a lot of that information was printed, but there was nothing stamped on the nameplate from the factory, so we had to go find a catalog or a specification sheet. Today, pretty typically power factors on there, so I can get an idea of what, at least at full load, my power factors of my motors are. Operating below the nameplate will reduce that operating power factor. So power factor changes with load. You can see at full load, at 50% load, my power factor has dropped significantly. So there's my penalty, that curve there, for oversizing a motor with its operating power factor. I have found that if you go to motor spec sheets or the catalog, a lot of motor folks today will give you their quarter, half, and 3/4 load power factors in the spec sheet or in a catalog. So if you know this motor is operating at 50% load, and maybe only once for 20 minutes, 30 minutes in the day do we take it to full load, I can get a feel for where it's going to operate at each of those loading levels when I change the load on it. So a rated horsepower of a motor goes up, power factor will generally go up on average. Large motors have nameplate horsepower power factors are better than small motors. I just gave you some examples here. Fractional horsepower motors I looked up in the database range from 42 to 72%. Okay, so you can find some pretty low power factors on fractional horsepower motors. 1 horsepower 3-phase 230/460 volt power factor range for all the motors available right now to buy in the US market, about 65 to 80%. You see, going to 1 horsepower increases that whole range quite a bit. 100 horsepower 3-phase, 76 to 90%. So those are the ranges that are available in the market. You can see some pretty significant differences here in terms of the high and the low in the market out there for power factor. Lighting and power factor, another one of those issues to watch. LED lighting systems can vary from really low to very high levels depending on manufacturer. Customers that don't pay attention to power factor when purchasing fluorescents and LEDs have seen large increases in their power factor adjustment. Believe you me, they're not very happy when they say, what, the utility gave us money to reduce our kilowatt hours, but now our power factor adjustment went way up? Nobody told us about that. So attention to power factor specs when purchasing LED lighting systems can significantly reduce the potential for having low power factor in a plant. Now, Hoosier Energy and the member co-ops require high power factor fluorescent and LEDs that they will rebate. So if you've gotten a rebate from Hoosier or the co-ops for an LED retrofit or planning to, you don't have to worry about that like some other clients I work with at other utilities. Hoosier says in order for you to get your rebate, your LEDs have to meet the DLC criteria, the Design Lighting Consortium. The DLC criteria says to be listed on their list, the power factor has to be 90% or above. So Hoosier will only rebate DLC listed lights. So you're pretty sure if you did a rebate project and Hoosier paid a rebate or the co-op paid a rebate, you've got good stuff, high power factor stuff. Okay? But not all utilities are like that. So manufacturers of LEDs can reduce power factor by adding RFI and EMI filtering if they don't pay attention to the overall design of their device. So what we've seen happen is LEDs generally, when they first were starting to be commercially available, were pretty good at power factor. Then they had a lot of complaints about my LEDs producing a lot of noise and messing up wireless signal systems in my facility, in my plant or building. Very common for that noise coming off the LED to interfere with my FM communication system, my wireless system, things of that nature in the plant. And so manufacturers started putting filtering, noise filtering into their LEDs, and if they're not careful in that process, they can drop the power factor significantly. That's really what's going on in the market today. If they do a good job of design, they cannot affect the power factor much at all by adding the noise reduction. Okay? So power factor of LEDs today can vary from 30% to 98%. And I'd rather be towards the top of that range than putting in a whole bunch of 30% power factor LEDs to drag my plant power factor down now when I put those in. Just to give you a feel, 2 different standards out there that people look at. So Energy Star, the government program that everybody's probably familiar with, that labeling of equipment, LEDs above 5 watts should have a power factor greater than 70%. So the government says, okay, we're going to call Energy Star power factor above 70% to qualify. The DLC list, as I said, considers 90% and above as the minimum acceptable. So even Energy Star is quite a bit lower than the DLC criteria that Hoosier essentially requires you to buy from to get your rebate. The other thing to remember about the lighting part of power factor is that dimming LEDs reduces power factor. So there are a lot of LEDs with dimming strategies that cause a reduction in the operating power factor below full light output level. So that's another thing to watch. That reduction isn't linear and accelerates the lower the light's dimmed. This is some data on the light output, power use, and power factor for a pretty common 50 watt LED in the market. You can see at 100% light output, power factor's pretty good. We get down to 50% light output, we're down to 21.3 watts input, the power factor's fallen to 82%. And when I go down to 20% dimming, or 20% of full light, I'm down to a 40% power factor, and at 10%, I'm down to 22. So that becomes important. If I'm going to dim LEDs for very long periods, I want to make sure my controller and lamp work together to not have a huge reduction at the level I'm dimming it to on power factor. Another one of those things that we've started to see more of, particularly as people have been seeing really good deals on imported LEDs putting in facilities. So that becomes another one of those things. An LED with a 95% power factor at full light could have a low power factor when dimmed to 50% or the half light level in the facility. Improvement of correction. Okay, we said we've had the amps lag the volts. We need to speed the electrons or amps back up in relation to the voltage. We could put capacitor banks on the transmission system, and some utilities do, to correct in general for that part of the system. Co-ops can put capacitor banks on their distribution system, and many do, to correct for part of the variations. Not uncommon to see a residential subdivision that has a capacitor bank out going into that subdivision to correct for all the residential homes. Capacitors and or VAR compensators can be added to the electrical system by the customer, and that targets the location of the source of that low power factor equipment. And as I said, the explanation now is instead of paying the utility to provide that reactive power, we're providing it ourselves from our capacitor bank. So we no longer have to pay them to provide that reactive power. That's how you explain it, make your business case. And if we do the calculation, typically you as the customer can buy the power factor correction capacitors and install them cheaper than you can buy it from the utility, the reactive power. So managing motors, pay attention, we said that. Fractional horsepower, not much you can do except buy at the upper end. If a problem, lots of fractionals, power factor correction. Large motors, buy at the upper end, size them near their nameplate horsepower so they have a high operating power factor. Some plants use synchronous motors that have a power factor of 1 to try to get away from the problem. That's another option. If a problem, power factor correction of some type is typically the go-to means to raise my power factor. We talked about lighting. Make sure your LEDs are above 90%. If you want to get the rebate from the Hoosier and the co-ops, you got to do that anyway. If I'm dimming, look at the power factor of the LEDs at various dimmed levels corresponding to the light that you might dim it to in your plant, just to see what it does. Many times, people today don't pay attention to the controller and the LEDs for dimming. Is that, well, it'll work, it'll dim the light, fine, it does what I want to do. Certain controllers work better with certain LEDs to maintain higher power factor when they're dimmed. So we're seeing an effort by LED folks today to try to start telling people, match your dimmable controller with your LED so power factor doesn't get so low. Then the question becomes, do I install my correction at the offending equipment or do I put it at my main service? And again, back to what I talked about earlier, that's a little bit of a, okay, if I'm going to put it at the offending equipment, I might want to do that for 3 or 4 things in my plant that are the big offenders. And now it makes sense because when the motor goes off, the capacitors are disconnected, they're not overcorrecting. And when the motor comes on, the capacitors are energized and they're correcting. So that works really well to match my needs. Then, I might decide that I want to do it back upstream. That could be another option. Okay? So, if I have a whole bunch of things, equipment, circuits to put them on, I might go back out to the main service. Instead of putting in 150 power factor correction capacitors on 150 devices, it's probably cheaper to go to the main service with a panel full of capacitors and a controller that stages them. So it monitors your power factor, and if it gets low, it kicks in the right amount of power factor capacitors. And then you turn more equipment on and it goes a little lower, it kicks in more. And when you turn that equipment off, it sees your power factor go up, it disconnects power factor correction capacitors to try to match your load. So this can be automatic where it's switched on in and out as needed in stages. I have seen some plants that run 24 hours a day, their power factor is just always low, it doesn't go up and down much. They just make it fixed, it's always wired in. So those are options. Static and dynamic VAR compensators are now power factor correction capacitors on steroids. That's the way that I like to describe them to people. We take normal power factor correction equipment and we put better electronic controls with it that can respond to changes in power factor faster and more precisely than a capacitor. That's the idea here of these devices. When you hear about VAR compensators, power factor correction with better response time and more precise response. Okay? So they respond faster, but they're more expensive than mechanically switched capacitors. This is not so much to correct power factor, but respond to fast changes in power factor when they occur and cause a voltage sag. So one of the things that happens, this happened and why these things became popular in certain segments of the industry, is if I bring in a portable car crusher to a junkyard, and that junkyard is a mile down the road from your plant. Every time they start crushing a car in that car crusher, what happens to the current on the distribution co-op distribution line? Goes up. Crushing the car, I need more amps to crush that car. And now all of a sudden, it's only there for 30 seconds, 40 seconds, the car's crushed, and then it goes away. And during that time where those big amps and the inrush of that car crusher hit, that voltage could drop quite a bit. And all of a sudden you're complaining about voltage sags from your co-op. They're potentially causing electronic controls to trip or lock up. So the VAR compensator is fast enough to see that current shoot way up, power factor shoot way down, that causes the voltage drop, and connect the right amount of VARs into the system really fast so that you don't see a mile down the road at your plant nearly as big of a voltage drop when they start the car crusher motor. So the static VAR compensator works really well if that load that's cyclic on and off is always the same. The dynamic device is even more expensive, and that becomes important if the car crusher is crushing a really flimsy vehicle and then a 68 Lincoln Continental is the next vehicle. What happens to the voltage drop on the system between crushing or when they're crushing each of those cars? It's not as big on the flimsy car. So now the dynamic VAR compensator can compensate for the different amounts of current each time the car crusher hits. There are lots of other loads like a car crusher that can do the same thing, but that's one that a lot of people can relate to in terms of why do we care. So Static and dynamic VAR compensators might be marketed to you if you're talking to a power factor correction consultant simply because they're more expensive and they do more. The only time you really need to look at these is if the power quality voltage sags that go along with some big motor starting in the system also needs to be mitigated. So these take, and they will mitigate power factor. They act like power factor correction capacitors. They just do it faster and more precisely. They're more expensive. So the economics. What charges adjustments do I pay for? What does it cost me to correct? How fast do I break even? This is the business case. This is the thing we got to talk to the business folks and say, what are we doing? So you did a study at your facility. You can increase the typical monthly power factor from 82% to 91%, and it's going to cost you $14,000 installed for the power factor correction capacitors. Your meter demand is typically about 780 kW. So without power factor correction, 780 times the 0.97 divided by the 82% power factor, I'm paying for 922.7 kilowatts. By putting in the power factor correction, I take the 780 times the 0.97, divide it by my new power factor, and I'm paying for 831. That's a difference, a drop of 91 kilowatts I'm paying for on the demand charge on my bill. Okay, that's $913 a month at $10 per kilowatt times 12 months. That's $11,000 per year. It cost me $14,000 to put in. I'm saving $11,000 a year. I'm not sending the utility. I pay for that cap bank in about 1.25 years. Pretty decent payback. There's that business case you're making to those financial people in the company that says, hey, it makes sense for us to pay for $14,000 of equipment installed to not pay $11,000 to the utility each year going forward. That's a pretty good deal, right? Are they going to like a 1.28 year payback? Yeah, this is a really, wish we'd thought about this before. And that's the idea with power factor correction. Okay, so once we know what the power factor is that we're starting from, and how much capacitors we need, that tells us how many capacitors. Pretty straightforward to get to what's my installed cost for that equipment to do. We do the calculations, it says what can we save, we get a payback. And most utilities have set their power factor adjustments up such that almost probably 95% of the time when I talk to consultants all over the country, it's cheaper for the customer to do this than the utility to do this. So this tends to be then one of those things that lots of customers look at and find those paybacks are really good. So a couple other now caveats about power factor correction. I told you the good stuff first. What do we need to watch out for? Because there is no magic black box, right? So now, when I put power factor correction capacitors in, I have to be careful about nuisance VFD tripping from capacitor transients. Every time I start or stop a capacitor, energize or de-energize, more correctly, it produces an oscillatory transient voltage spike. An oscillatory because it rings, positive and negative, and slowly decays. So it decays typically in less than half a cycle. But that oscillatory transient from turning the capacitor on or off is a very, very common high voltage trip error message on VFDs. So I've worked a lot of plants where 8 out of 10 times when they put the capacitors on or off, certain VFDs trip in the plant. And the error message on these trips from an oscillatory transient from energizing, de-energizing a capacitor is always a high voltage error trip message on the drive. So that's fairly common. I have seen some of these drives trip from capacitor energization and shutdown 17 miles away in a substation. from the customer. So those oscillatory transients can move quite some distance. But historically it's been, we put new power factor correction in and now we have drives tripping. And so that becomes an issue to watch if you have lots of drives, things of that nature. On and off creates that. It can cause drive trips. I said high voltage trip error. Even utility substation or distribution line switching can be a problem. So how do I ride through that and make sure my VFDs are not going to trip when I put my new capacitor, power factor correction capacitor stuff in? Well, I can put those drives on a UPS, but that's expensive. I could have a motor gen set where the motor of the motor gen set absorbs the transient, doesn't get through the mechanical back to electrical conversion. I could use line side reactors or chokes, and that's become kind of the main first go-to if I have issues with VFD tripping from turning on and off power factor correction capacitors. So I put a line side reactor or choke in front of that drive. And what that line side reactor or choke does is dampen that transient. It doesn't filter it completely out, but it clips it so that we don't get the big peaks here. And typically that's all you need to do is clip those peaks off with the reactor, dampen it enough, and your drive trips go away. And line reactors or chokes aren't very expensive compared to some of these other options. There are some people that have had some success using a transient voltage surge suppressor. So the idea was, well, that's a spike, that's a voltage transient or spike. I'll use a surge suppressor to mitigate it. The problem tends to be that many of these oscillatory transients from capacitor banks aren't big enough to hit the level where the standard surge suppressor is going to now suppress. So if it has a low level of surge suppression where it will take and suppress that, it can work. If it doesn't, a lot of people have said, well, reactors or chokes are the cheapest, best, fastest thing that we can do there, as we're seeing out in the market today. So an oscillatory transient problem, textile knitting mill in South Texas we worked with was experiencing numerous drive trip problems. Sometimes all the drives tripped, sometimes only a handful. The trip errors were high input voltage, classic. They're blaming the utility for spikes. We're going in and thinking there's got to be power factor correction probably most likely somewhere in this plant. Where is it? The plant electricians had told management the utility's giving them dirty power. And so they had recently installed, when the trips started happening, a staged power factor correction system that automatically adjusted the amount of reactive power as load changed on site. Each time caps in the system were switched in and out, that oscillatory transient was produced with the potential for overvoltage conditions on the drive. They put line reactors after the caps, after their staged power factor correction device, so that those oscillatory transients couldn't move past the line reactors to get downstream to any drives. And that essentially took away their problem. Now the other issue is that drives don't like capacitors, and drives produce harmonic distortion that can mess your capacitors up. So drives and capacitors don't play well together. So capacitors should be carefully analyzed and detuned to avoid problems from harmonic distortion from equipment in the plant. That resonance creates heating and reduced life in the capacitors. I've seen it to where it produces enough vibration that the capacitors vibrate and tear the mount up, and pretty soon the capacitors fall off the mounting brackets or bolts and are laying in the bottom of the panel, or worse. So this is another fairly common issue. So capacitors that are resonant or tuned to the characteristic large harmonic frequencies of a VFD, typically the 5th and the 7th, have a high potential for failure or rupture of the capacitor. So the 5th and 7th harmonic frequency are very, very high typical harmonic frequencies from a VFD. Murphy's law says when you size your power factor correction capacitors for your optimum correction, the resonant frequency of that capacitor, where it's going to start vibrating, is with the 5th or the 7th. Okay, so that's a problem. So how do you address that? I make sure when I put up a capacitor bank that it's not going to resonate at one of the harmonic frequencies that's high in my plant already, from VFDs or computers or LED drivers or various things like that. So look at that resonant frequency and make sure it's not the same as something that's big already in your plant from existing equipment. The harmonic frequency or order that the capacitor bank will resonate at is the square root of kVA of the system, which is the short circuit capacity of the system in kVA. You can figure out that from the transformer size and the voltage and the impedance, and the kVAR rating of my capacitor bank at the system voltage. So my example, we have a 1500 kVA transformer with a 5.5% impedance and a short circuit kVA calculated as 17,391 amps. So if there was a direct fault on that transformer, it can deliver 17,931 amps through that fault, at least until an overcurrent device somewhere clears the fault. We have a 350 kVAR cap bank that our consultant is proposing we install for power factor correction. I run the numbers through, the square root of 17,391 divided by 350, and that comes out perfectly at the 7th harmonic frequency. What are one of the two biggest frequencies from a VFD? The 7th. Okay. So I have a potential problem in that sizing that bank at 350 kVAR with the electrical characteristics of that transformer mean that if I give much 7th harmonic frequency that could be already in my system from drives into that cap bank, it's going to start vibrating, or worse. So that becomes a problem. So now what I want to do, if I end up having one at the 7th or the 5th, one of those problematic harmonics from VFDs, I want to resize this cap bank so I end up on an even frequency. 2, 4, 6, 8, 10, an even number. Because in a three-phase electrical system, the even harmonic frequencies cancel each other out. So you can have all the drives in the world you want in your facility, and you shouldn't have even order harmonic frequencies. So, does that make sense? I size my cap bank so its resonant frequency is an even harmonic, and I know I'm not going to have a problem with vibration now in doing that. And so if I adjust that slightly, I can adjust it so the math gives me the 6th or the 8th. And now I know I'm not going to lose my cap bank because of harmonics from my drives in my plant. That's the other side of the capacitor VFD coin. The capacitors send transients that can trip the drives. The drive sends harmonics back upstream that can rupture the capacitors. They do not play well together in plants.